I'm just going to do a quick demonstration with the oscilloscope. So I've actually got, that's a microphone right here that's plugged into the input, and I've got a set of tuning forks over here, and you can actually see that my voice is registering on the screen there. That's the waveform of my voice. Notice that it's very jagged, if you can see that, but every time I talk you see this sort of jagged waveform. Now compare that with the wave, actually I'll just zoom in a little bit more. Now compare that with the wave from this tuning fork here. So you can see it says 512, that's 512 hertz. Okay, so let's have a look at the tuning fork and let's see how the waves compare. So you notice that it's quite uniform. It's not jagged. It's just one sort of, it's almost like a continuous sine wave. There you go. So that's 512 hertz. Now, just for comparison, let's look at another tuning fork. So this one here is, what does it say on it? 341 to 343 hertz. So that means it's got a lower frequency. Let's have a look and see what that one looks like. So you notice again there's a uniformity to the wave in terms of the appearance of the wave, but you'll notice that the wavelength is a little bit longer. So the higher frequency, the 512, so this is the 512, that one the wavelength was a bit shorter, and the lower frequency, which was the 341 to 343, the wavelength was a little bit longer. So it's an inverse relationship. So as the frequency goes up, that means that the wavelength gets shorter. As the frequency goes down, that means that the wavelength gets longer. So one more comparison, let's go with 256 hertz here. That's this guy here. It's the longest one of the bunch. So again, we see a uniformity to the wave in terms of the appearance, but you can see the wavelength is even longer. So it's got a smaller frequency, it's going to have a longer wavelength, and that just comes from the wave equation V equals F lambda. V for sound in air is roughly 343 meters per second. So that means that if that's going to be constant, that means F times lambda has to be constant. As one goes up, the other one must go down by the same factor. Alright, so just move the camera a little bit closer. So we notice the jaggedness of the waveform when I talk. So you've not really answered the question, well, why is my voice, why does it have this jagged waveform, whereas the tuning forks have this very sort of nice uniform waveform? And the answer to the question is that it's because my voice contains a lot of different frequencies. I'm not just speaking in one frequency all the time. If I was, it would also be quite uniform. It's actually a lot of different frequencies that are combined together. So to illustrate this, I'm going to take several different tuning forks and I'm going to hold them next to the microphone, and we'll see what happens as we add the different frequencies together. We won't necessarily get the exact same, most likely won't get the same exact waveform that we have here when I'm talking, but we're going to get something that resembles it. So let's try the first tuning fork. So that's two together. So that's two tuning forks at the same time. And let's see if we can get three. So a little bit difficult to do as a single person to try to get three going. But you did notice that as we add more and more frequencies in there, the waveform does become a bit more jagged.